Now let us see with this, start with this impulse invariant transformation. How this impulse invariant transformation has been obtained. How this formula has been arrived at. Okay. Now since the name is mentioned as impulse invariant. And here we are going to make use of the impulse response concept. We have to convert analog filter into a digital filter, for which we are deriving the transformation technique formula for it. In impulse invariant, how this conversion of analog filter into digital filter transfer function occurs is given as a block diagram. Sequence of step is represented here. Yes, how it will be done is, you have to consider from analog filter transfer function, I have to get the digital filter transfer function, which is h of z, h of s to h of z. And how this is obtained is, if I first I have to take inverse Laplace transform of HA of S, which is the analog filters transfer function. If I take inverse Laplace transform of HA of S, we are going to get HA of T, which is nothing but the impulse response in time domain. Impulse response in time domain. Okay, and once we got the impulse response in time domain, that is, this is a continuous time signal. T represents a continuous time signal. This impulse response is going to be continuous. Now we are going to convert this analog into a digital value, which means this continuous signal has to be converted into a discrete value and then to a digital value, right? So as you know, the sequence of steps for analog to digital conversion is sampling, quantization, and coding. How this is being done is, HA of T, which is a continuous time impulse response, is sampled uniformly. This HA of T is sampled at every t is equal to nt seconds. The t is called as the sampling period. And if this is sampled at t is equal to nt, we will get h of nt. If t is equal to 1, usually we will be considering t as 1. This can also be approximated as h of n. Okay, so the formula for impulse invariant transformation is obtained by following all these sequence of steps. H of s, we are going to take HA of s, we are going to find its inverse Laplace transform. We will be getting this HA of t. Once we get this HA of t, you have to sample this HA of t at t is equal to nt to get this h of n. And once we get this h of n, if we take z transform of h of n, we are going to get h of z. So this is how analog filter will be converted into digital filter in case of impulse invariant transformation. So the technique, basic technique that we employ for this conversion is called as sampling here. So whenever we go for sampling, it is always associated with some problem like aliasing. Until and unless you choose the sampling period to be greater than or equal to twice the maximum signal frequency, we are going to end up with aliasing. So T should be taken very high if I want to avoid aliasing in this case of impulse invariant transformation. So this is one drawback of impulse invariant transformation. In impulse invariant, we may get the problem of aliasing. That is, this aliasing problem can be overcome in bilinear transformation. This is one difference between IIT and BLT. Okay, you can make a note of this also. Why in impulse invariant we are getting aliasing is because of this reason. We are going to transform HA of t into h of n. That is, we are going to sample HA of t at t is equal to nt to get this h of n. Okay, so HA of t is nothing but the impulse response of analog filter. T is the sampling period. H of n, we know it is the impulse response of the digital filter. And this h of n can be obtained by sampling h of t at t is equal to nt. That is what is we have written here. The same thing is being expressed. H of n is obtained by sampling HA of t uniformly at t is equal to nt seconds, where t is called as the sampling period. Okay, these are the steps that we are going to follow to arrive at the formula. Now, first step is we have to consider h of s. And then the first step, h of s. Find its inverse. you will get h of t. Sample it, you will get h of n. Take z transform of h of n, you will get the digital filters transfer function. We are going to follow the same steps. So we have considered an analog transfer function, HA of S. This is the analog transfer function. And this analog transfer function is expressed in such a way that it has n distinct poles by means of partial fraction expansion. We have expressed this HA of S as sum of n distinct poles. I is equal to 1 to n AI by S minus PI. So this is the initial step. This is the HA of S that we have taken into consideration. Okay, for which we have to transform, or we have to find what is H of Z. Okay. Next, once we get this HA of S, we have to find the inverse Laplace transform of it to find the HA of T. So if I take inverse Laplace transform for HA of S in the left hand side, I am going to get HA of T. And what is the inverse Laplace transform of 1 by S minus Pi? Do you remember? S minus Pi, 1 by S minus Pi. What is the inverse Laplace transform of this? It is e power Pi t. Only for e power Pi t u of t, you will get the Laplace transform as 1 by S minus Pi. Hope you remember all these. This is the standard formula for e power Pi t u of t. If I take Laplace transform, we will get 1 by S minus Pi. So if I take inverse Laplace transform for this term in the right hand side, summation and this constant remains the same. Summation constant ai is being written here for 1 by S minus Pi. Since the inverse Laplace transform is e power Pi t u of t, we have represented it as e power Pi t u of t. Now the second step is also over. We have considered a analog transfer function. We have found the inverse Laplace transform of it. We have done the two steps. Third step is we have to sample this HA of t at every t is equal to nt seconds to obtain h of n. So wherever you have t, you have to replace it as nt to get this h of n. That is what is done in the this particular step. So h of n is HA of nt, which is equal to summation I is equal to 1 to n ai e power Pi. You have t here, so this is nt replaced as nt. Again you have t here, replace it as nt. Wherever you have t, replace it as nt. So in this step, we have sampled HA of t at t is equal to nt to get this h of n. Sampling is also over. Once sampling is over, if we have to find Z transform for this impulse response of digital filter to get h of Z. That should be the next step. So if I take Z transform of this, now this is the equation. So for this equation 4, we have to take Z transform on both sides. H of n, the Z transform will be h of Z. Likewise, here they are making use of the formula directly. So for h of Z transform of h of n is h of Z, for which the actual formula is summation n is equal to minus infinity to infinity h of n z power minus 1. Z transform formula ஞாபகம் இருக்கு இல்லையா உங்களுக்கு? Now I have to substitute h of n here and find its Z transform. What is h of n? H of n is the summation value. So here h of Z is equal to summation n is equal to 0 to infinity. Why the limit is being changed from minus infinity to infinity to 0 to infinity? Because you have u of t. U of t always exists only from 0 to infinity. Unit step signal exists from 0 to infinity. So you can change the limit from 0 to infinity. And I'm substituting h of n. H of n is the summation entire thing. Summation I is equal to 1 to n ai e power pi. What we can do? Summation I is equal to 1 to n ai e power pi nt z power minus n into 1, because u of nt is 1 in this interval. From 0 to infinity, u of nt is 1. So this is what we will get. Now ai and this summation are constant. Take this outside this n summation. We are interchanging the order of summation here. Make a note of this. The summation I is equal to 1 to n ai can be written outside and this summation can be brought inside. So it will be summation I is equal to 1 to n ai, summation n is equal to 0 to infinity, e power, you have n terms, group all the n terms, e power pit z inverse power n. It can be grouped like this. Okay. Now, if you observe this summation, it can be simplified by using what is called infinite geometric series formula. You are remembering this? Try to recollect. All these you have studied in Z transform. Infinite geometric series formula. Now, what is this infinite geometric series formula? It is summation n is equal to 0 to infinity a power n is 1 by 1 minus a. So what I can write instead of this summation, it will be summation I is equal to 1 to n ai 1 by 1 minus a power n. In the place of a, I have e power pit z inverse. This will be the h of z, final h of z. So we have done all the sequence of steps. We have taken a h of s as sum of distinct poles. That is, we have expressed h of s by means of partial fraction expansion with sum of n distinct poles. We have taken inverse Laplace transform for it. And then we have sampled this HA of t uniformly at t is equal to nt. Finally, we have taken z transform for h of n and we have obtained h of z. So we started with HA of s and we are ending with h of z. If I compare this equation with that of this equation, what we can observe? What can be observed here? If we compare, this is HA of s and this is h of z we have obtained. First step we have taken analog transfer function. The last step we have obtained digital transfer function h of z. So if we compare these two, I can say that 1 by s minus pi is now being transformed to 1 by e power pit z inverse. This is how we are arriving at the formula for impulse invariant transformation. So whenever I want to convert an analog filter transfer function into a digital filter transfer function, simply I can make use of this formula. 1 by s minus pi should be converted into 1 by 1 minus e power pit z inverse. We can apply this transformation alone, formula alone, and we can simplify by substituting the value of pin